Um, an augmenting path is a path in the residual network, right? Do we have, let's see, do we have any path that we haven't used? We don't, right?
I guess every option you encounter an edge that is maxed out.
Yeah. Yeah, here we cannot go, right? We don't have any more paths. We can't go here, right? We can't go there. Well, we can go there, but then we can't go there. So we don't have any more paths.
What's the capacity between D to T?
D and T, it was 10.
Okay.
Then we actually messed this up, right? It should be.
Yeah, we lost them.
Should we-
Yeah, this should be 5 and minus 5.
Yeah.
And we don't really need to be keeping the negatives since they are the flows, but I like them this way. Does this idea make sense? Reasonable sense. Still need to do one more at home, but and we talked about this stuff, right? The value of the flow F equals the net flow across the cut, right? And so my it's the net flow across the cut. So we get the duality, right? For any flow and any cut, the value of the flow has to be less than the total capacity from A to B. Right? For any cut and any flow, the value of the flow has to be less than the total capacity because we are sending data through all of those edges, right? We are sending data from one region to the other. So if this was our cut, my capacity is 28, right? I can't send anymore. And so my min cut is my max flow, which is the augmenting path theory says a flow F is a max flow if there is no augmenting path, and the max flow min cut theorem says the value of a max flow is the capacity of a minimum cut. And slightly stronger, the following three conditions are equivalent. For any flow F, there is a cut such that the capacity of AB equals the value of that flow. Saying that's the same as saying that F is a max flow, and that's the same as saying that there is no augmenting path with respect to F. Isn't that cool? now we can do other stuff. How long does this take, right? Well, given that my capacities are integers between 1 and c, the maximum capacity, right? And that throughout the algorithm, since all my capacities are integrals, the flow values and residual capacities are also going to be integers, then the algorithm is going to terminate in at most n times c iteration. Each augmentation increases the flow value by at least 1. And so the running time for Fulkerson is O(m)(n)c). M is the number of vertices, n is the number of m is the number of edges, n is the number of vertices, and c is this max capacity, right? So it's pseudo polynomial. If c equals 1, the running time is O(m)(n), right? It's pseudo polynomial, right? It's not polynomial in input size. It is pseudo polynomial. When you do this stuff, if you do your paths the right way, you do less iterations. So there is a ton of research on how to choose paths, right? We chose by random, but the idea is you could choose the augmenting path so that you can find augmenting paths and you have fewer iterations. Some heuristics use the maximum bottleneck capacity, the fastest, because that will increase the size of your steps, but you may still need to undo them. So. Or just a sufficiently large bottleneck capacity, or having the fewest edges. The capacity scaling algorithm, the intuition is let's try to get the one with the highest bottleneck capacity because it increases my flow by the maximum number. However, finding the one with the highest bottleneck capacity may take too long. So rather than that, maintain a scaling parameter delta and only considers those arcs with capacity greater than or equal to delta. And so what is going to happen is that we can half our delta. Once we find nobody with capacity greater than delta, then we half our delta. And we keep going that way. And that gives us nice logarithmic-ish stuff, right? So the outer while loop repeats 1 plus log 2 of c, actual ceiling of log 2 of c. There are at most 2m augmentations per scaling phase. And so we are going to end up in m squared log of c, which is better. We are gonna skip this stuff and skip this stuff. There is more and more possibilities, right? For how to do it in different conditions. Now, there is one cool thing simple unit capacity networks. If every edge has capacity 1, and every node has either exactly one entering edge or exactly one leaving edge, will be a simple capacity unity network. And the idea is that we can do stuff like bipartite matching by cheating and putting it as a network like this. And my C is 1, so that's actually good for my algorithm. Okay, let's go look at how to put it as a bunch of other things that can be, there it is. How can we apply this network flow? It's applicable in a bunch of things. For example, in bipartite matching, right? Given an undirected graph G, B, E, a subset of edges is a matching if each node appears in at most one edge. So what we are trying to do is finding a max cardinality matching. In a bipartite matching, the nodes can be partitioned into two subsets, L and R for left and right, such that every edge connects a node in L to one in R. So if all your edges go from one set to another set, and there is no mixing, right? This is very common when you really have two different kinds of things in your graph, right? So this is schools and students who are applying to those schools, right? And so the edges are this student wants to be in this school, or this school wants this student, right? And so you cannot have this school wants this school, right? That's a completely separate piece of the problem. Or the student wants this student. Those are different problems. They appear in match.com, not in here, right? It would be, would something like match.com or something like that have this? Maybe, right? As long as there's no bisexual people, right? But, so usually you can approximate and do those kinds of things. How does the bipartite matching have anything to do with this max flow? Well, I create a new graph, add an S and a T, put all my edges with infinity as the value that they have, and put unit edges, so ones from S to every one in L, from R to T is 1, and this infinity is really a weird number. It's an infinity that you actually can keep track of and say, oh, I have 3 infinities. So actually, in some other formulations, they just use a 1, which is the same thing. It's just I'm using it. It could be just bigger than the number of edges, right? And so you're never going to have more than that. So that's what infinity really means. It's not infinity as in infinity. And so the maximum cardinality of a matching in G is going to be the value of the max flow in this G prime network. Because given the maximum matching, what's going to happen is that we are going to have a flow sending one unit here and infinity here and one here, right? It doesn't matter what goes in here. That's why we can use infinity, because we have ones here. So it's going to be the same thing in a way, right? And this is a very common technique on algorithms, just transform one problem into another problem. So in order to do bipartite matching, we just do network flow. And actually C is 1, which is good. A perfect match has each node appears in exactly one edge. So when does a bipartite graph has a perfect matching? We definitely need size of L equal to size of R. But what other conditions do we need? What conditions are necessary? What conditions are sufficient? Can you think of other necessary conditions? What about the edges, right? What's the minimum number of edges that we need? L, right? Or size of L, size of R. Could you do a graph where you guarantee me that this happens? Just allow everybody to match everybody, right? So you have a complete graph for everybody in L, right? It's not complete. Every node in L with an edge to every node in R, and you can get a perfect matching as long as you have size of L equal size of R, right? It is slightly better. We have this, let S be a subset of nodes, and N of S, the set of nodes adjacent to that subset, so that is the set of nodes that can be joined, that have an edge. And if a bipartite graph has a perfect matching, then the size of the neighbors is going to be greater than or equal than the size of this S for every subset of L. And that is because each node in S has to be matched to a different node in N of S. And so if you don't have this, there will be nodes in S that have no match. Right? For example, this example, S is 2, 4, 5, and NS is 2 prime and 5 prime. That means that 4 and 5 can't match. There's only one element in R that can match with those two. So that's a necessary condition. And this shows that this is a sufficient condition. And this is Hall's theorem. So a bipartite graph has a perfect matching if and only if the size of the neighbors of S is greater than or equal than the size of S for all subsets of S in L. And it is basically a cut, right? Since we want the size of our matching to be, right, the size of L or the size of R, that has to be our mean cut. And that is basically the proof of Hall's theorem with a lot more math. But, for bipartite matching, fault-Fulkerson algorithm is order of M of n, Mn, because C is 1. And there are other algorithms that can do it a little bit better. Or potentially better depending on other things, right? This one is n to the 10�7 better than Mn.
Why does that L have a wave?
I'm hoping that it's a typo. Because if not, I mean, they do. I don't know what that O with a wig is. I would need to go look at the paper. Is that better than Mn to the half? Depends on M versus N, right? Given an undirected graph, not necessarily bipartite, can you find a matching, right? And so there is a bunch of algorithms for this kind of stuff that are similar. This is important in math. This would be another example, right, for K regular. So basically imagine a hackathon between Harvard and Princeton, or KSU and Georgia State. And you have exactly K friendship, right? Every Harvard student is friends with exactly K Princeton students, and each Princeton student is friends with exactly K Harvard students, friendship is mutual. And so can you arrange, can you make an arrangement so that every student programs with a friend, right? Every K regular bipartite graph has a perfect matching. So yes, you can. The size of the max matching is going to be the value of the max flow. You could put it as the flow is 1 over K if there is a matching, or 1 for S and T. And that would give us a perfect matching. Disjointness of paths. Two paths are edge disjoint if they have no edge in common. Can you find the maximum number of edge disjoint paths? well, happens to be related, right, to the max flow problem, right? You can assign unit capacity to every edge, and the max flow is equal to the maximum number of edge disjoint paths. Isn't that cool? It is not the same problem, but it's the same problem, right? Similarly, finding network connectivity, a set of edges disconnects T from S if every ST path uses at least one edge in F. And so this is the same thing as the disjoint ST paths, right? Basically, just take one from, right, since they are edge disjoint, take one from each one of those paths, and you get this. It gives you the number of edges that you need to remove. There's a similar thing in undirected graphs. You can do it by basically consider them as directed, but add one going and one coming back, which is basically, that is what undirected are. It's going to be different than if you had done directed, because now you have they can use, two paths may be edge disjoint in the digraph, but not in the undirected graph. So one could use the going, one could use the coming back, right? And so those are considered two different edges. In the undirected graph, they wouldn't be. But however, for these, in any flow network, you're going to have a maximum flow which has either going or coming back to be zero, which is cool, because that gives me the same thing for the undirected graph. And so I have this in German or Dutch or something like that. Given an undirected graph with two nodes S and T, the max number of edge disjoints ST paths equals the mean number of edges with removal disconnects S and T. Undirected graph, and now it's node disjoint rather than edge disjoint, right? Same thing, right? The node disjoint path is the minimum number of nodes that I need to remove to disconnect S and T. And it is the same thing in a directed graph. Isn't that cool? What can I do? What other things can I do with this? I could consider having multiple sources and sinks rather than one. What could I do? Well, what I can do is just create a new flow, right? And create a new node S and add edges with infinity going through. So that's not going to be my constraint. And the same for the nodes that had that were sinks, I'm going to send them all to one sink. So I end up with an equivalent network which will have equivalent flows. So it doesn't really add much. However, this adds a little bit more complication, and this is almost what you think you come from here. You can have a minimum flow that is a demand. So now a circulation rather than a flow is a function that satisfies oh yeah. Now my in and out are not equal to 0, but they are equal to the demand of that node. Now we can do it the same way, adding a new source and a sink. For each vertex with demand less than 0, add an edge from S to that vertex with capacity minus demand. And for each vertex with demand greater than 0, add an edge to this T with that capacity, and that gives me the same, basically the same thing. There is another theorem. If the summation of the demands for a partition exceeds the capacity, then I will not gonna have a circulation. So that's basically the same thing as the cuts. Now we can add even more. I can add lower bounds rather than 0. So here, instead of having 0, I have L of E. Do I have a feasible circulation? Basically, what I can do is treat the lower bound as increase it as demand on one side and decrease it as demand on the other side. And that will force me to send that much. Let me super quickly go over some other examples. This is mainly to get you into the idea of, oh, now I have a problem, can I map it to something that looks like something that I saw, right? And that's what they do. Survey design. Design a survey asking N1 consumers about N2 products. You're assuming that you're asking them one survey per product. It may be, right? You can only survey the consumer I about product J if they own it. You can ask the consumer I between CI and CJ questions or give them that many surveys. And you want to ask between PJ and PJ prime consumers about product J. Your goal is to design a server that meets these specs if possible. It would be a bipartite perfect matching when CI and CI prime and PJ prime are 1. So you can only ask one question about one product to a customer. And you only want to ask one customer about your product. We could make it as a max flow formulation, put all your consumers on the left side, your products on the right-hand side, add edge, IJ is the consumer J owns product I. Add edges from S to every consumer J. Add edge from product I to T. Add edge coming back from T to S. And consider it as an integer circulation. Isn't that cool? Airline scheduling. Airline scheduling is a big, horrible mess, right? Which is why when computers go down, Delta doesn't fly, right? And it happens once a year for one of the airlines, right? You want to be as efficient as possible as in terms of equipment usage. Planes are really expensive. You want to have them in the air as much as possible. But you also have to do maintenance and stuff like that. Crew allocation, pilots and stewards and stewardesses are also very expensive. At least they used to be. I don't know if they make money anymore. They used to be expensive. And so again, you want to have them occupied within constraints of you don't want them to be flying for 24 hours straight and stuff like that. And you want customer satisfaction, and you have stuff happening, like weather and stuff. They are maybe not one of the largest, but they were one of the first guys that started using this stuff. I don't know if they are the largest, one of the largest anymore. Depends on how you define large. A toy problem would be to manage flight crews by reducing them. Your input is a set of K flights for a given day. Flight I leaves origin OI at time SJ and arrives at destination DJ. And you want to minimize the number of flight crews. For each flight, include two nodes, UI and VI. Add source S with demand -C and edges S and UI with capacity 1. And a sync T with demand C and edges VI and T with capacity 1. For each I, add an edge UI VI with lower bound and capacity 1. And if flight J is reachable from I, add another edge VI UJ with capacity 1 and lower bound of 0. And go to town. A circulation will give you the solution to the problem. It is complicated enough and then has nothing to do with the real world problem, right? On an airline, you have a lot more stuff, right? And yeah, you get this kind of libertarianism, right? The problem is union regulations. The problem is not that you don't want pilots to be flying for 12 hours because they'll crash the plane, right? The problem is the union regulations. You get constraints, right? Stuff like, right? There is a limit of how much performance you can get, how much time you can get in a given day out of a person. You have longer planning horizons, not just one day. Deadheading, sending somebody but not scheduling them back has a cost. And then shite happens. And you're also trying to optimize for money. Most of these algorithms start, right? A lot of these problems start with something like this, and then they add tons of heuristics and constraints and things like that for their own algorithm. But they usually start with something like this. This can also be applied to image segmentation. I'm going to skip it. Can be applied to project selection, where you have prerequisites. And so your project has a revenue PV that could be positive or negative. In order to do a project V, you also need to do project W, so you'd have prerequisites, and that's why you would do stuff where you lose money. I need to do this so that it enables me to do this other project. And so finding this subset, finding the group of projects that maximizes revenue is a flow problem. You can think of it as open pit mining. You're trying to extract blocks, and you cannot extract block B without also extracting W and X. This looks exactly like a video game. And it is also similar for stuff like this, where you get, oh, can this, you have 4 teams, can they still make it to the final? Right? Who could win? Given this, it is obvious that Montreal cannot win. They have 77. There is still 3 more to play, so the max they could do is 80, and so they're not going to win against Atlanta. Philly, however, cannot win either, although it's not that obvious, and that's because New York and Atlanta are going to play 6 more, right? Games. So either one of them has to get to at least 84, which means that Philly is also doomed. So this kind of stuff is also a flow problem that interests you. Go look at the example in the book. Isn't this cool? So now we saw how to solve max flow problems and how does it apply to a bunch of problems that don't look necessarily related, right? What this should really tell you is that there is a gajillion problems in HackerRank and Top Coder and all those interview things that map to this one, right? So get into how do you map, because that's going to be important both for programming interviews and maybe, depends on what you're doing for work, for actual work, eventually in 5 years. Any questions? Cool. Then I will see you eventually on Wednesday.